With one-slit interference, you'll find that many of the principles from two-slit interference remains exactly the same. In fact, many times teachers start out with one-slit interference. I personally like to start out with two-slit interference because I feel like it's a little bit easier to understand, specifically because of the concept of what happens right here. Now, if you divide a single slit into an infinite number of points, each point inside of space, inside the space inside the slit, actually becomes a brand new point source. That's a principle that I either taught you in class before this video or there was a video right ahead of time. And it's somewhat of a confusing one because if you have light incident on a single slit, you might just think that you're just going to get a nice diffraction pattern where it comes out, spreading out like that, and then you get a solid red that then fades off into darkness. But that's not the case. You actually do get an interference pattern with a single slit, assuming the single slit is small enough, because as the slit grows larger, the interference pattern begins to disappear. What's actually occurring is if we divide the slit width b in half, b over 2, and we give infinite number of points. Here I just chose to divide it up in 5 equal parts, or into 4 equal parts, excuse me. Here's my 5th point. Between any point and its corresponding point on the other half. So here I chose the top one from the bottom half and the top one from the top half. So I chose 2 points that are perfectly corresponding. You know, this point and that point would correspond, and then the middle one again to the bottom one there would correspond. So from any 2 points that correspond between the 2 halves, then you're going to have a phase difference caused by a path difference. Let me explain. Let's take this top point. Distance length L must be traveled from this top point to here I have a minima, the first order minima, or the dark spot. If I choose the exact same corresponding point on the bottom half of the slit, remember each point inside the slit becomes its own brand new point source, almost like each point was another slit. So I choose the corresponding on the bottom half, here that one is. For a dark spot to occur, a minima, it must travel, this path length must be L plus 1/2 lambda. Right? If we were going to go up to this next one, right, and I called that length L from the top one, then from the next corresponding one, it would have to be 3/2 lambda, so forth and so on, continuing up. Notice the path difference for destructive interference, the minima, 1/2 lambda. So whenever I write that into my equation, just like I did with double slit, sine theta, here's my triangle. I redrew the triangle here, right? There's the triangle, redrawn, right triangle under small angles, that is approximately a right triangle. Sine theta equals your opposite, that's 1/2 lambda, divided by your hypotenuse, 1/2 b. Now in the double slit, it was just b. We were dealing with the entire slit, but because of how this works, whenever you're thinking about corresponding points in each half, if you will, to cancel each other out. In other words, this point cancels that point, this point will cancel this point, and this point once again cancels that point to give you complete destructive interference. You're actually dealing with 1/2 b there for the hypotenuse. So sine theta equals opposite 1/2 lambda divided by hypotenuse 1/2 b. Your 1/2s cancel out. Sine theta equals lambda over b. And so for a minima, you end up with lambda over b. If I want to make that from first order, second order, third order, so forth and so on, I can put an n in front of that. I can go into a little bit better derivation for that later on. But theta equals n lambda over b. Now, take note here. That was the equation for the maximas with two-slit interference and diffraction gratings. With one-slit interference, it's just for the minimas. Now, I'm actually not going to give an equation for the maximas with one-slit interference. It's a little bit more complicated because the maximas don't follow the exact principles. It's close, but it's not exactly what we need it to be. So I'm not going to talk about the maximas. They actually have different widths as you go, and that's one of the reasons that things get thrown off. But here's the equation to get to the minimas, the dark spots for single slit diffraction. Now, just like in double slit diffraction, here's an equation using this small triangle right here, but this angle, it's not overly useful. But this theta that comes in that small triangle, it's that top angle right up there, is actually the same as this angle right here, and a right triangle drawn from the center of the slit up to the point that we're talking about here being the first order minima. Using this triangle, I can write an equation. Tangent of this angle equals opposite h over adjacent d. So here's that. Small angle approximation means I can drop off the tangent. Theta equals h over d. And the combination of these two equations, just like with double slit, is what allows me to solve easily for things that actually matter, where theta is your connecting part. You can measure h, measure d with a meter stick rather easily. H might be a little close, so you have to look carefully, but still measurable with a meter stick. Solve for theta. Then you can plug theta in over here. Which order number did you go up to? First order, second order, third order, so forth, so on. Or if you were going down, first order, second order, third order. Which order did you go up to for n? B is the slit width, the entire slit width, right? And lambda is the wavelength of light you're looking for. So if you knew B, you could solve for lambda. Another thing that I want to mention about this is the intensity of light. The central maxima is going to be very bright. So an intensity graph, you're going to have a very high peak, very bright. And then each one as you go grows very dim. In fact, with single slit diffraction, the intensity drops off very rapidly as you go. So I just wanted to point out an intensity graph, how the intensity continues to drop down rapidly with each maxima as you get further and further away. Working an example problem here for you. I'm going to have a light from about 650 nanometers, that's in the red part of the spectrum, passes through a person's eye and is focused on the retina. And we're going to treat the eye like a rectangular slit, but if we were to quickly summarize what actually happens, you have a hole, if you will, in your eye. Now there are lenses and other things, never mind that. We're going to try to simplify the eye, the human eye down. You have a hole, which is a pupil, and you have a screen in the back of your eye, the retina. Now granted, that screen is curved. We're not going to focus on that right now. The distance from the pupil to the retina is about 24 centimeters, and the pupil can expand, it can contract depending on the amount of light. At this moment, it has a diameter of 5 millimeters. So 24 millimeters over to the back, that's the retina, and 5 millimeters is the diameter of the pupil, or B in this case. What is the distance from the central maxima to the first order minima? So from here to here. What is H is what we're looking for. And once again, we're going to treat the pupil as a rectangular opening. We'll get to circular openings here soon. Now notice here, I know what we had labeled H, 24 millimeters, D, 24 millimeters, and we're looking for H. So if I knew theta right here, then I could easily solve for H. Tangent of theta equals opposite over adjacent. Small angle approximation can drop off the tangent. But I don't know theta, so at first I need to solve for theta, and we know the equation here in single slit diffraction for minimas, theta equals n lambda over b. Now that's the same, that's almost, really it is, the same equation for maximas and two slit interference. Different principles applying, don't get confused here, just because the equation looks the same. So if you need to remember it this way, the maximum equation for two slit and diffraction gratings becomes the minimum equation for single slit. So theta equals, I'm going to my first order, lambda, 650 nanometers. That's 650. Nano means times 10 to the negative ninth. Not worrying about putting it in proper scientific notation. My calculator will take care of that. If you're reporting in scientific notation, you need to make sure it's in proper scientific notation. Millimeters, 5.0 times 10 to the negative third because of the milli part there. And whenever I plug that into my calculator, remember we use the small angle approximation, I come out with 0.00013 radians. Now that I have the angle, I can actually set up into the tangent. Remember, small angle approximation, so we're able to drop off the tangent. Theta also equals h over d, and some people will purposefully set those two equations equal to each other, right? These two equations, because they're both equal to theta. So you could say n lambda over b equals h over d, which is a fine thing to do if you're making small angle approximation. I just personally choose not to, because I like you to have the understanding of what the angle is. Plus, you'll find in some colleges, especially whenever the angles start to get close to the small angle approximation, this is kind of a problem, that it might be better not to make it, because notice my screen and my slit width are actually relatively close, so in the same order, so that starts to worry me a little bit there. But my angle is small, so theta equals h over d. So plugging in now, 0.000123 13 equals h over my 24 millimeters. Remember, 20 milli times 10 to the negative 3. Multiply that over and you get h. My final answer comes out to be 3.12 times 10 to the negative 6 meters, aka 3.12 micrometers, is the distance from the center of the central maxima into the minima, the first order minima. Now that's going to become important as we continue to go along and we start talking about resolution of objects.